Okay, so here is the thing about calculus. So we have learned how to differentiate the simple function like x squared, x cubed. We have done sine of x. We also have done some polynomials, and we feel pretty good about ourselves. Then someone puts in front of you like what will be the derivative of sine, argument is x squared, and you freeze. That is exactly what we are going to fix in this lecture. By the end of this lecture, that the expression will feel easy for you. In fact, every complicated derivative you will ever encounter, and honestly, in most of the mathematics and science, you will do for the rest of your life. Here comes the idea, that is the general. So let's start what is general. So here's a fundamental issue. Most functions you encounter in the real world are not simple. They are not simple. Let's take an example here. 3x minus 1 to the power 5. Sine of x squared. The square root of 1 plus x squared. So we see that the functions are built inside other functions. Think about the temperature and altitude. Temperature depends on altitude, and altitude depends on time. So the temperature depends on time, but through two layers. Or you can think about how a camera's shutter speed depends on light level, which depends on the angle of the sun, which depends on the time of the day. In mathematics, this idea has a name: composition. And the chain rule is a tool that lets us differentiate any composed function systematically every single time. Because what I'm about to show here is one of the most used formula in all the calculus. So before we can use the chain rule, we need to be crystal clear on one concept, which is the function composition. A composed function has a form, this: y equals f of gx. There are two functions working here, one inside the other. This gx is the inner function, and f gx, I'm here using the dot to represent gx here. This is the outer function. So it is 1 on the out function. So here is a key insight, and I want you to really sit with this. The outer function does not know, or it doesn't care what the inner expression actually is. It just treats the whole thing as a single chunk of input. Imagine gx, this as a black box. The outer function f just receives a number from that box and does the job. So this mental model is everything you need for the chain rule. Okay. So let's practice identification. Because if you can correctly identify the inner and outer function, then you are already more than halfway done. So first, identify inner versus outer. So let's take an example here. Y equals 4x squared plus 8 whole cubed. So what is the outermost operation happening here? The outermost operation here is raising something to the power of 3. That being cubed is 4x squared plus 8. So we name it the inner function 4x squared plus u. If I say this 4x squared plus 8, if we name this as u, then the outer function will be equal to u cubed. So y is equal to u cubed. Okay, so you need to ask yourself, what is being raised to the power? The substitution variable u here is just a label for the inner expression. You can take any variable, u or a v or any variable. So here's the question I want to ask yourself every single time. So what is the last operation that would happen if I computed this expression by hand? For this y equals 4x squared plus 8 to the cube, the last step would be cubing. So cubing is the outer function. So this works every time. Okay, so last operation is the outer function. Last operation is the outer function. So let's drill this identification. I'll give you here 4 functions. For each one, I encourage you try by yourself. You pause this video and then write down your answer, then you come back. Ready? Okay. The first one is y equals 3x minus 1 to the power 5. Let us go through them together. First, y equals 3x minus 1 to the power 5. The last operation is raising to the 5th power. So the outer is equal to u equals, outer equals, if you find this 3x minus 1 is u, then it will be u to the power 5. The inner equals 3x minus 1. Similarly for the second one, so we can write 1 plus x squared, the square root is equal to the power 1 half. So last operation is half power. So outer function is u to the power half. Inner is 1 plus x squared. For the third, y equals sine 4x cubed. So last operation is taking sine. So outer equals sine u, inner equals 4x cubed. In the fourth one, we have y equals 1 over x squared plus 1 cubed. So we can write x squared plus 1 to the negative 3. So the last operation is the negative 3 power. The outer function will be u to the power negative 3. And inner function will be x squared plus 1. Okay, so you need to notice here, correct identification is half the battle. Okay, so this is crucial. All right, so here it is, the chain rule. If y equals f of gx, then the derivative dy dx equals f prime gx multiplied by g prime x. Let's maybe read this in plain English. The derivative of the outside function, the derivative of the outside function evaluated at the inside, the derivative of the outside function evaluated at the inside times the derivative of the inside. Okay, so this first expression is the derivative of outside evaluated at inside multiplied by derivative of inside. Okay, so in terms of Leibniz notation, we can write dy dx equals dy du multiplied by du dx. Here y equals fu and u equals gx. So look at here, this du and this du almost look like they cancel. They do not literally cancel. They do not literally cancel here because these are derivatives. These are not fractions. But this mnemonic is perfect for remembering the rule. The intermediate value u changes the two rates of change together. That is a deep intuition. If y changes twice as fast as u and u changes 3 times as fast as x, then y changes 2 times 3, which is equal to 6 times as fast as x. So that is the chain rule. A rate of change multiply. This is why the rule works. And understanding this is what separates students who remember it under pressure from students who forget it. Right? And this is a picture here that makes the chain rule completely concrete. Think of 3 stations connected in a line. X on the left, u which is equal to gx in the middle, y equals fu on the right. When x changes by a tiny amount, u changes at the rate gx. So when u changes, y changes at rate f prime u, which is equal to f prime gx. The chain of rate links here x all the way to y. This is literally why it is called the chain rule. You are chaining together the individual rate of change. So before we start examples, let me give you the 3-step recipe you will use every single time. The first is differentiate the outer function. Treat the inner expression as a single block. Do not toss it yet. Keep the inside the same. So write the inner expression unchanged inside your answer. Multiply by the derivative of the inside. Now differentiate the inner expression and multiply it on. Okay, so outside first, inside stays. Multiply by inside's derivative. So I'm going to say that like a mantra every time we do an example, because repetition is what builds the muscle memory that will carry you through exams. Let's do our first example here. Here is a example. Differentiate sine. In the argument you have a polynomial function x squared plus x with respect to x. So step 1 is the outer function is sine function. Yeah. So different sine and you will get cosine. But the inside stays locked. Do not toss the inside. The Second step is the inside x squared plus x goes in exactly as it is inside the cosine. So I have written here cosine of x squared plus x, not cosine x. The inside has not changed. This is where many students slip up for the first time. Now the differentiate the inside. So inside is x squared plus x. Differentiate inside x squared plus x, which will be exactly equal to 2x plus 1. Now multiply both. So that you'll have cosine of x squared plus x multiplied by 2x plus 1. Done. Okay, so let me repeat once again. Derivative of the outside, which is cos, inside stays the same, which is x squared plus x, times derivative of inside, the derivative of x squared plus x is 2x plus 1. So 3 steps, 1 answer every time. So we have another example here. Y equals 3x minus 1 to the power 5. So this is a power with compound base. 3 step. So what is the first step? Outer function is u to the 5. Derivative of u to the 5 is 5u to the power 4. So we can write here 5, here u is 3x minus 1 to the power 4. Okay, so the formula, power rule formula, bring the 5 down, reduce the power by 1. Bring the 5 down to the base here and reduce the power 5 by 1. So second step is we have the inside function is 3x minus 1. It appears unchanged inside the parenthesis here. And then derivative of inside, which is the third step, the derivative is the derivative of 3x minus 1 is simply 3. Okay, so just multiply 5 times 3 is 15 times 3x minus 1 to the 4. So you may notice here, I did not expand here, 3x minus 1. So I can write here as it is. So at the beginning, I did not expand this 3x minus 1 to the 5 before differentiating. That would give 10 terms before even I start. The chain rule collapses that into a 3-line calculations. So that is the power of this tool. It keeps complicated expressions intact. All right. So another example here. We want to differentiate this square root function. So 1 plus x squared to the power half. 3 steps. First, outer function is u to the power 1 half. Here u is 1 plus x squared. So I'll write here derivative of this one. Derivative of outer function is 1 over 2 u to the power negative half. So 1 over 2 u is replaced back 1 plus x squared to the negative half. So inside remains the change. That is second step here. And third step is derivative of the inside function, which is 1 plus x squared. Derivative of 1 is 0 and x squared is 2x. Simply 2 and 2 cancels out. So the resulting expression will be x over square root of 1 plus x squared. Right? So every square root problem with the composition inside follows this exact pattern. Rewrite as a power, apply the chain rule, and then simplify. Okay? You will use this pattern constantly. So here is a type of problem that trips a student up in the exam constantly. What if you do not have a formula? What if f and g are only given as a table of values. The chain rule exactly the same. So if y equals fx, then at point x equals a, the derivative is y prime at point x equals a is equal to f prime ga multiplied by g prime a. So the three steps lookup strategy is here. You find ga from the table, use ga as the input to find f prime, look up f prime at that value, and the third step is multiply by g prime a. So the critical realization is f prime is evaluated at f prime is evaluated at not at a, remember. So the input shifts, the input to f prime is ga, not a. So this might be the common mistake in table-based general problems and exams. Okay, so there might be common mistake here. So you have to think carefully about where each numbers come from. Okay, here comes the trigonometric functions. So trigonometric functions appear as the outer layer in all composition all the time. The pattern is completely standard. Derivative of sine u equals cos u multiplied by u prime. Derivative of cosine u equals negative sine u multiplied by u prime. So the structure is identical to the power rule example. Differentiate the trigonometric function first. Keep the inside the same and multiplied by the inside derivative. The negative sign in the cosine function here, the negative sign in the cosine derivative here, it comes from the trigonometry, not from the chain rules itself. The chain rule just appends the u prime factor at the end. So you need to memorize this too. So they will appear in like physics, in engineering, in signal processing, in periodic functions. You will differentiate. So in machine learning also, these are inside the activation function of neural networks. Every time you use AI, these derivatives are running underneath. Okay, so notation matters. Notation can be treacherous, like sine to the power 4x and sine x to the whole 4 look similar, but they are completely different functions. Sine to the power 4x means sine x to the power 4. Sine power 4x means sine x to the power 4. The sine is computed first and then the result is raised to the 4th power. The outer function is raised to the 4th. The inner is sine. But sine x power 4 means the sine of x to the power 4. The outer function is sine. The inner is x to the power 4. So my advice, before you differentiate anything, you need to rewrite it with explicit parentheses until the structure is unambiguous. So do not trust your eyes alone. Trust the parentheses. Okay, here is one example here. Y equals sine 4x cubed. The argument here is 4x cubed. Step 1 is outer function is sine u. Let's say 4x cubed equals u. Differentiate, then it will become cosine of u. So I'll get cosine of 4x cubed, replace back, u equals 4x cubed. So inside it stays the same, it is unchanged, which is step 2. And the step 3 is derivative of this 4x cubed, which is equal to 12x squared. So multiply. So the answer has two parts. Cosine of 4x cubed multiplied by another is 12x squared. So both must be there. So if you write only this cosine of 4x cubed and stuff, you have forgotten the chain rule. So the 12x squared is the inside derivative. It must always appear. The factor is non-negotiable. Okay, so chain rule plus product rule here. So now things get interesting. What happens when you have a product of two functions? And each of them is also a composition. So we use the product rule first. I hope you are familiar with the product rule. The product rule is if you have two functions f and g, so simply derivative is f remains the same, derivative of g, plus g remains the same, derivative of f. So each derivative may still requires the chain rule. We apply the chain rule whenever we need to differentiate f or g. So here's an example, product of two functions. One is trigonometric sine function, another is some algebraic function here. So if I use this as uppercase fx, like before here, and this is gx, uppercase g, x is sine x, then use the formula. So it remains the same, derivative of sine x, cosine x, plus this remains the same, sorry, sine x remains the same, derivative of this one. So we use chain rule here. The chain rule here is 3x squared plus 1, it remains the same. Bar will be 3 minus 1, which is equal to 2, and the derivative of inside function, which will be equal to 2x. So this look messy, but every piece comes from a rule, you already know. Product rule on the outside, chain rule inside. So rules compose, just like function do. Stay organized and you'll never get lost. So what if you have 3 layers? The chain rule generalizes, you peel the layers one at a time from outside moving inward. Outside layers, for example, you have outside layer which is fifth power, derivative 8, you'll get power 4, inside stays. Okay, so you can chain arbitrarily many layers. Right, so this is chain rule plus quotient rule here. If we have the function, we can say the rational function like fx over gx, we call this the quotient rule. So first we apply the quotient rule first, and then we use chain rule inside. The process is similar. So there are multiple layers. If a function has multiple layers, then you can differentiate layer by layer, as I said earlier. So before we close, let's zoom out here. The chain rule is not a calculus trick. It is a fundamental principle of how change propagates through layered system. For example, in physics, velocity, acceleration, and energy chain together through the time and space. And in economics and biology, business cycle and population dynamics are system of composite rate of change. And machine learning, the propagation, what we call the back propagation algorithm, the engine of every neural network, every large language model, every AI system, that we use today is the general applied to a composition of potentially millions of functions. The fact that AI can recognize images, translate languages, and holds conversions exist because of the general. So you know how fundamental this formula is. So here is the survival guide for hard problems. So identify the top level structure. Do not expand. Differentiate in layers. Seek the inner expressions. Okay. So most mistakes are organizational, not conceptual. So this is the general. Remember these four steps. Practice it until it is automatic, and you will be able to differentiate anything the course throws at you. And if you ever get stuck, come back, go slowly, label your parts, and remember rate of change multiply. Okay, thank you for the video.